right. Welcome everyone to the final talk. So I'm super happy to welcome Wojciech Czerwinski. I think most of you know him. If you're in any way interested in reachability problems, you'll probably know of his recent results. So in 2013, he did his PhD at the University of Warsaw. Then he did, I think, a one-year postdoc in Bayreuth, Germany. And yeah, so most of you probably know him from him being a major figure in the recent stunning advances in fast reachability. So first the non-elevated lower bound and the Ackermann lower bound. And so I'm very happy to have him here.
Thank you, Georg, for the introduction, and thank you for inviting me. Yeah, so recent advances on reachability problem on VASSes, and to say this on the by sequence of examples. I think this is maybe how it's the best, or how I can the best to present you techniques. No, not necessarily present you all proofs till the details or something like that. So I would like you to give a feeling of that. I will introduce basic systems and so on. What is the problem about, and a very short history. And then I will go into three parts. First part will be about big reachability sets in vector addition systems, which I abbreviate as VASSes. So this is a well-known family of examples since many years, but I want to give you intuition that you can implement something complicated in VASSes by very simple examples. So that's just. I will give you some zero testing technique, which was used in this recent progress, and then at the end, I would like to give you some interesting fact about pushdown VASSes, which I mean, there is still an open problem for pushdown VASSes, and this may be a starting point to think about it. So maybe I should comment. So I gave recently invited talk on CONCUR about with similar title. So I, for those of you who have heard it, I made some effort to say about something else. So these two parts will be different. Yeah, and introduction is similar. And I would be happy to take questions. So I originally was planning to talk about one more technique, but I decided to throw it out, not to be forced to speed up. So if something is unclear, disturb me. Okay. So what are vector addition systems? I will actually present them as vector addition systems with states. So I abbreviate this as VASSes. So by examples. So I define examples. So these are just finite automata with some number of counters. Here you have 3 counters. And these counters have integer values. What is important, non-negative integer values. You never can drop below 0. And what the transition does is it changes counters. So it can increase or decrease counters by fixed amount. So for example, let's say this transition, it increases the first counter by 2, decreases the second counter by 1, and doesn't touch the third counter. Okay. Here I have colored these transitions, but there is no semantics. This is just for better illustration. Okay. So these are just such automata. You can think multi-counter automata. And what is important, you have no zero test here. You cannot have a transition which can be fired only if something. If some counters happen to drop below 0, this run is killed. It's not a valid run. Okay, so let's have a look at some example. So this is not a random example. This is an example from Hopcroft Pension work from 78, and that's a meaningful example. This is like first counter example you think for many conjectures, and this is also a starting of our. This is a first hard example. You will see that there is already something interesting in this example. But let's look at the example run. So here is a configuration. I call this a configuration, which consists of states and counter valuation. Let's say you start from such a configuration. And what you can do, you are here, so you can, for example, fire this transition. Yeah, so you decrease first counter by 1, you increase second counter by 1, and you don't touch the third counter. And you can do it next time. Yeah, you can fire this transition one more time. And then what you can do, you can, for example, use this black transition and jump without changing any counters to the state Q. And here you can fire, let's say, this transition twice, and you can fire a red transition, and you are back here. So this is an example run. But it's also an example of what you can actually do here, because you see, so by applying this blue transition, you can think you actually transfer value from first counter to the second counter. Yeah, you decrease this one, you increase this one. So you transfer this 2 to the 2 in the second counter. You are not forced to transfer it fully, but you may do. So what you may do is, if you start from 207, you can transfer this 2 to the second counter, jump here, and here you can think this is about this transition as transferring value back from second counter to the first counter, but at the same time you multiply it by 2. Yeah? You decrease this counter by 1, increase this by 2. So here you transfer this 2 back into first place, and you have now 4 0. And you jump it here back. Yeah? So you see, I hope you see what happens. Okay, so I should comment with vector addition systems or vector addition systems with states, they are essentially equivalent to Petri nets. Many of you may have heard about Petri nets. That's, yeah, I think just that different presentation. But formally speaking, like most of the problems are polynomial reducible, you know, from Petri nets to VASSes and vice versa. So okay, so let's have a look one more time at this example. So if you start any counter valuation in any configuration of this form, pk0n, in this example, you may fire this transition k times. You know, here I write this as a single transition, but it's a sequence of transitions, of course. Transfer this value k to the second counter, go via black transition here, apply this transition k times, so transfer this k to the first counter, you have 2k here, and come back here. And this transition, this red one, is the only one which touches the third counter, decreases it by 1. So from pk0n, you can go to p2k0n minus 1. So start from, so you can decrease the third counter. You pay say by decreasing third counter for the option of multiplying the first counter by 2. In words. So here you can do the same. If you start from P01 n, you can multiply first counter, multiply it n times. And then you go into something like that. I hope it's clear. And one more time about this example. So if you are here, you can fire this transition, you know, any number of times in between 0 and 2 power n. So you can go into 2 power n minus a and a for any a in between 0 and 2 power n. So each such configuration can be reached. So I call a reachability set. What is a reachability set? Set of all the configurations which are reachable. Here you can see that at least exponentially many configurations can be reached. And actually, set of reachability set is finite in this situation. So we have an example of finite exponential reachability set, exponential size. Okay, that's not true. What you will see, you will have bigger reachability sets. You may ask, okay, why the reachability set is finite? You can see that red transition can be, you know, the only transition which touches the third counter is this one. So the red transition can be fired only n times. And from some time on, you will never be able to fire it anymore in any run. So then you can only stay here, go there, and stay here. And here you can stay for a finite amount of time because this counter is decreased, and here as well. So any run is fine. Actually, okay, so that was just like a warm up. What is the reachability problem? You know, but let's say you are given a VASS. This is how I abbreviate vector addition system with states, and two configurations. S stands for source configuration, T stands for target configuration. Yeah? And you just ask, is there a run from source configuration to target configuration? Okay. So short history of research on this problem. So it's already asked, I think, in the beginning of 70s. And first, so here I present just a milestone result about complexity of the reachability problem. First result was by Litton in 76. So he has shown exponential space hardness, actually of some other problem of coverability problem, but it implies space hardness of reachability problem. So it was actually strong. But still, decidability was unknown, and I've heard the conjecture that it's undecided. But a few years later, Meyer have shown decidability of the problem, and you may know that the construction was very complicated, and therefore some work followed. Like that was a try to simplify, to phrase, this construction in words which are easier to understand. So then these works follow, and this construction is now known sometimes or often under the name of KLM decomposition, or Kosaraju KLM. Okay, and then
There's a question.
Oh, I'm not sure. I think it doesn't matter. I think for both exponential space hardness works. You agree? Okay, so here, I mean, there were works on VASSes, but no milestone result, let's say, about complexity. I mean, no concrete progress on complexity, as we can see. Say I want to mention this work in 2015. It was about fixed, so VASSes in dimension 2. This is how I denote the dimension. Yeah? 2 VASSes. So here, these guys, Bolden and al., they have shown that the problem for dimension 2 is p-space complete. So this is actually very interesting work. I will tell you more about fixed dimensions later. And then pretty recently, Jerome Leroux and Selvan Schmitz have proven first upper complexity bound, cubic Ackermann. If you don't know what is this, it's some exotically huge upper bound. It just, there is some concrete bound, but it's bigger than Ackermann. And then a few years later, they made a progress. So here I can maybe tell you, it was just by analyzing the KLM decomposition algorithm. They realized it works in such a time. Then they improved it a bit, modified it, and then the improved one works in Ackermann. And in the same year, we managed with co-authors to prove a tower lower bound. So the point is, And then there was still a gap between tower and Ackermann. So two teams independently managed to prove Ackermann hardness. One was Jerome Leroux, and one was me together with my colleague from Warsaw, Łukasz Likowski. We used a bit different technique, but based on let's say both were based on techniques which were introduced here, and both were using a technique of multiplication triples, which I hope to show you today. Yeah. So my talk is about these lower bounds. I would like to show you how you can construct complicated vector addition systems. It's about a feeling, how you can encode hard things. Okay. So maybe I should. Okay, I would like to define this Ackermann. I think many of you know what is this, but let me define it quickly. So it's if I like definition by fast-growing hierarchy of functions. So you can define function fk. You can define function f1 of n equals to n. So this is just doubling function. And if you have a function fk, you can define function fk plus 1, next one, in the following way. Fk plus 1 of n is just a composition of many fk's, how many n here, applied to 1. So if we have this, we can see what is f2. So f2 is just f1, so doubling, composed n times, applied to 1. So if you double 1 n times, you have 2 power n. So now if we have f2, what is f3? You exponentiate 1 n times. So you have f3 is a tower of exponential of size n. And you can see f4 is something already crazy. And Ackermann function, also sometimes called f omega, is defined as fn applied to n. So you can see it grows faster than any f fixed fk. And what is cubic Ackermann is f omega cube. Just to have a feeling something higher. Yeah, so based on these functions, you can define hierarchy of complexity classes. So complexity class, let's say bold fk, is a set of problems which can be solved in time or space. Roughly speaking, fk. You make the class robust. And similarly, class of problems in Ackermann. Okay. So concretely speaking, so we have proven the Ackermann hardness, but more concretely, what was the lemma? So the current best statement is that the following: a reachability problem for VASSes in dimension 2k plus 4. Yes, this is how I denote the dimension. Is fk hard. So this statement is actually by Jerome Lerner. So this is so in particular, by that reachability problem for VASSes is fk hard for any k, which means it's not perimeter recursive. Yeah. So this is how we show Ackermann hardness. And actually, so this is a best, say, the lowest dimension in which fk hardness is currently known. We have shown with Łukasz dimension 6k. Jerome originally also have shown some higher dimension. And the current, let's say, open problem is, can we manage to get fk hardness in dimension k plus constant? You cannot go below dimension k minus 4. This is known. And this is like a open problem in this field now, but you may see this as very in-depth, but it's also interesting. But okay, so I think at this point you can ask, okay, so I'm presenting you some piece of research which solves open problem, but okay, what is the future? So I would like to convince you that we solved some problem, we fixed complexity, but it's not end of the way. I think that we rather, combinatorics of VASSes, of VASS runs, I think it's still very mysterious, and you have a lot of striking open problems, many huge gaps, and we still don't understand. And I would like to convince you about this in next slide. I think next slide. Yes. So the question is everything solved? My answer is no. I will give you 3 examples. What if you look at reachability for 3-dimensional VASSes? For 2-dimensional, there was this result about p-space completeness. For 3 dimensions, of course, you have p-space hardness coming from dimension 2, but the best upper bound is complexity class F7, so much harder than tower. So it still can be tower complete, it still can be p-space complete. We have no clue. And you can see this is a big gap. So and you can see that this gap in complexity comes from gap in understanding. Even more striking is some problem which Georg mentioned to me a few years ago. And I was trying to solve it, and I think Georg as well, and I think other people probably as well. So reachability for fixed VASSes. So in reachability problem for VASSes, you input VASS, source configuration, target configuration. But you can fix VASS, and your input can be source and target. So then for each VASS, you have a different problem. So for some VASSes, problem is very simple. If you have no transitions, then target is reachable from source if they are equal. Yes. If you have all the transitions, then you always have reachable. But for some, it may be hard. So the question can be how hard this problem can be. And initially, you may think, well, it should be probably Ackermann-Hart, as the general problem is Ackermann-Hart. But we were thinking for some time, and we actually think it might be in P space. So the gap is, in between, say, Ackermann and P space. We totally lack understanding of this. And I think this is very interesting. So, and the reachability problem is open for many VASS extensions. So there are some natural extensions of VASSes, branching VASSes in which runs may branch, push-down VASSes. So VASSes in which you have additionally a push-down, data VASSes. And in all these extensions, reachability problem is, I think, conjectured to be decidable, but no decidability is known. So here is even bigger gap. So you may see there are fundamental open problems in understanding this. So that's also my hope that these techniques which I present you are not only about the past, it's also maybe about the future. Okay, so start. So yeah, I will present you now an example of a VASS which has finite reachability set, but much bigger than exponential, actual size tower, and it will be very simple. So here you have the same example which I already showed you, but we have added the fourth counter. But nothing happens with the fourth counter. Here we have 0, here we have 0, here we have 0. Here nothing is written. It means this transition has 0 effect. I decided not to write 0, 0, 0, 0. Yeah, so here you transfer things from first to the second counter. Here you transfer back by multiplying, and here you increase the third counter. Okay. And we add one more state R, in which you have this transition. So you transfer from first counter to the third counter. And you have one transition like that, in which you increase the first counter, and this is the only place where you decrease the last counter. So let's see what we can do with this VASS. If we start with something like that, P10, K, and M, then first we can do what we did, in this upper part. So here we can loop K times, and we can multiply this 1 K times by 2. Yeah? So we can reach from 10 K, we can reach 2 power K 0, 0. No touching M. Yeah? This is just repetition of what we did before. Then we can, if we have this 2 power K 0, 0, we can go here and here to state R and use this loop many times to transfer 2 power K from first counter to the third counter. Yeah? And then we can go back here. So go to, this should be P, sorry. We can go to P10 to power K, and we decrease this counter M minus 1. Yeah, one more time, this should be P. So you can go from P10K to P10 to power K by paying, by decreasing the last counter by 1. So you can already see what happens, I think. If we start from 101N, you can keep doing this. You can have 2 power 1, and you can do this n times. So you can go into 10 tower of n and 0. And then if you have tower here, you can, let's say, follow this loop many times and decrease this tower to any number you like in between 0 and tower. So here you have a reachability set of size at least tower. And you can see that it's actually finite because this transition can be fired only n times. So then without possibility of firing this transition. You can fire this only finitely many times, and you can stay here also for finite amount of time. This is the same argument as before. So this is a finite reachability set of size tower with 3 states and 4 dimensions. And in general, you can do similar thing. With D plus counters, you can have finite FD size reachability set. So I hope you already see you can implement very complicated things in simple VASSes. And yeah, so but this was known for a long time. So in this VASS, you have very long runs, but somehow you are not forced to do it. You know, nobody forces you to really use it fully. I think I have it on next slide. Yeah, it's about enforcing. Okay, so one comment. So yeah, I would like to give you insight into this FD hardness, which we have proven for VASSes in some fixed dimensions. So, but observe that if we want to prove FD hardness, we definitely should have examples of VASSes in which there are no short runs. So if you would know, so imagine you have such a claim. If in a VASS from source, there is a run from source to target, then there is also a run from source to target of length at least at most tower, let's say. Then you can explore all the runs. Then you can answer a reachability problem quickly because you can explore all the runs from source of size of length at most tower. This is in space tower, and you can check whether you can reach target or not. So you definitely should have VASSes in which there is a run from source to target, but the shortest run is very long. So this is maybe first question which you can ask yourself. Can I construct, things in which you have only very long runs? And these examples are not sufficient. They somehow, the VASS is not forced to take the long run or to compute a big number, which are similar things, yeah. Because if you would be forced to compute the tower thing, then maybe you can add transition which decreases it, and you have a long run. So in this example, you have this run which goes to 1, 0 tower, but you may totally ignore this and just go by this transition, and this transition, and do such triangles and reach 1, 0, 1, 0. You're not forced to take it. And so we need some kind of enforcing techniques, which will be like some kind of techniques to simulate zero test. But you may think, okay, if you simulate zero tests in VASSes, it seems like you have VASSes with zero tests, and these are Turing powerful. So we will have limit. We will be able to simulate limited number of zero tests, but somehow similar. And one message is we will consider small dimensions. So this is a lesson which we learned from tower hardness and Ackermann hardness. So both stories of going to this results where we started from some observation in small dimensions. And then we learned on small dimensions how to design techniques which allowed us to get stronger results. So I will also show you some things in small dimensions. Yeah, so maybe one remark is that in VASSes, you already have very weak form of zero test. So in reachability problem for VASS, because if you ask, can I reach target from source? You ask, can I have a run which at the very end have some, let's say the target is all the zeros, yes? So you have 1, 0 test at the end of a run. So you may see these techniques which I present to you as boosting this one single zero test at the end of a run to many zeros. Yeah. Okay, so this is now just a notation. So we used to present automata or VASSes like that. Yeah, so this is an example of a VASS which transfers here the value from first to the second counter and then back here. So for example, if you start from n0, you can reach at most to n and 0. But there is another very convenient way of presenting VASSes. In many cases, much more convenient, is as programs. So on this example, you may write, you have two counters, x and y. x and y. And first you have a loop which decreases first counter x and increases second counter y. And then you have a loop which increases first counter and decreases the second counter. And I hope it's very natural what it means. So this is, I see this as not a different, system, a different presentation of VASSes. And I will present VASSes today sometimes like that. It's much easier than to write a code than to draw a complicated picture. Okay, so now I want to introduce this technique of multiplication triples. I still have 20 minutes. So the point, yeah, so this technique was used in our constructions. It was invented by Jérôme Leroux. So the idea is that if let's say you have some in your VASS, you might have many counters, but you focus for a moment on some free counters. And imagine at some point of a run, maybe initially you have some gadget which enforces values on these three counters to be like that, to be like b, m, and then b times m. So essentially speaking, some value, and multiplication of this value, of these two values. Then this has a big power. So this allows for zero testing, for limited zero testing. But for zero testing, concretely speaking, for m-half zero tests on b-bounded counters. What are b-bounded counters? So we say that the counter is b-bounded if we know that value of this counter along any run never will go above b. It's somehow guaranteed to be in between 0 and b. And yeah, you often deal with such a situation. Or sometimes you say that these 5 counters are b bounded if their sum is bounded by b, but this is not a much of a difference. So the message is that having such a triple is very powerful, and so essentially speaking, the whole challenge is to compute such a triple for a very big m, for very big b, and let's say very big m as well. But now I want to tell you that for small, and then, yeah. So in next slide, I will show you why this such a triple allows for zero testing. I will show you how this works. And the whole challenge in our lower bound results was to compute such a triple, such that we are allowed to zero test, to implement many zero tests. But for small b's, this is easy to construct a gadget we computed. So if b is, let's say, exponential, so you can represent it in binary. In transition, you can have one transition which adds b 0 0, and then in a loop you can add 0 1 b, and m is kind of guessed. It's a number of times you apply some concrete loop. So you can imagine a gadget which has first transition which adds this b on first counter, and then a loop which adds 0 1 b, and then goes out, and it always computes something of this from b, guessed m, and b times m. Do you see this? Should be maybe on picture, but so and yeah, I don't have time to say it, to phrase it fully, but it's not for long. Just believe me that if we get such a triple for b of size fd of input, this pretty easily gives fd hardness. Essentially speaking, it's known that counter automata, say free counter automata, for free counter automata, the following problem is fd hard. Is there a run in which all the counters are fd bounded? This is fd hard. So the whole challenge is to get this. And now I would like to show you how such a triple can allow for zero tests. I think this is really a nice trick. It can be helpful in your fields. So assume that we have some free counters which has some such a value, x, y, z. And let's say we have another counter which is called x prime. And I will show you. Okay, so we start from x plus x prime being b, yeah, 0 plus b is b, and we will keep this invariant. So we will keep x plus x prime equals b. Now I will show you how to implement zero test on this counter x. So imagine that we have a run, and in many times we fire this procedure, zero test, here, there, and at the end of the run we check something, and this check at the end of the run guarantees that all the zero tests were correct. This is like a framework. So how do we implement? First, you have a loop, the following loop. This loop increases x prime, decreases x. So you may think x is here, x prime is here, and you just transfer value from x to x prime. Yeah? And here you do something on z, you count on z how much you have transferred. I mean, this is how you should think about this. Of course, here x and z is not distinguishable, but you should think you transfer value from x to x prime, and z counts how much you transfer. Then you have next loop, which transfer back from x prime to x, and you decrease z by this, you count on z how much you have transferred. So these two loops are the following: you have x prime, you have x, you transfer something back, and z decreases by counting how much you have transferred. Okay? So let's notice now by how much z can be decreased. So here you have this x plus x prime, and you keep this invariant here. Yeah, x plus x prime is constant. So at most you could transfer, from the situation you have x prime is 0, x is b, you transfer fully the whole b, and you transfer back fully the whole b. So you can at most decrease z by 2b. Yes? And then you, at the end, you do decrease y by 2. So y is always by such a zero test decreased by 2. And z is decreased, as I told you, by at most 2b. Do you agree with that? And what is important is that it's decreased by exactly 2b if and only if x prime was 0, x is b, it was fully transferred and fully transferred back. So it was 0 at the beginning and 0 after. So now, at the end, so this is implementation of zero test. At the end of the whole run, you check whether z is 0, so the third thing, the one decreased here. And I claim that if z happens to be 0, then all the zero tests were correct. Why? So you can see, so y, counter y, started from value m, and in each zero test, it decreased by 2. So you can fire the zero test at most m half times. And each time you fire the zero test, you can decrease z by at most 2b. So in order to reach 0 from b times m, you need to, in each m half of zero tests, you need to decrease by exactly 2b, because 2b times m half, this is exactly bm. So the way, the z should travel from bm to 0, it should make the biggest jumps it can. And each jump should be of size exactly 2b. Is it clear? That's the essence of the trick. Yeah? So actually, if z is 0, it means that every jump was exactly 2b. So in each zero test, z prime was exactly 0. Yeah? So that's the trick. So here, some questions to this? So here I have shown you how to zero test one counter by such a triple, but you can actually test more counters. And I think this is also a nice trick. So I would like to present you this, because this is not a straightforward generalization. So here, so in this previous slide, in each step, y was decreased by 2, and z has this property that if our zero test was correct, then it was decreased by 2b. We could decrease it by 2b, and otherwise we couldn't. So here our goal is also to decrease z by at most 2b and by exactly to b if zero test is correct. So imagine we have k counters. Before we had 2, which sum up to b, and we keep this invariant. So now I would like to show you how to test any of these counters. So you might think you will have x minus 1 important counters and 1 auxiliary, one coming from the strip. So how to implement zero test on some counter, let's say x1? First, we transfer value from x2 to x1 and count it down on z. So this is exactly this loop which I have shown you. Yeah, you decrease x2, you increase x1. So we transfer thing from x2 to x1, and you decrement z. Yeah, so this is a macro for that. I prefer to write this instead of that. So what you do first, you have x1, x2, x3, and so on. You first move things from x2 to x1. Then you move things from x3 to x2. Then you move from x4 to x3, etc. And at the end, you move from xk to xk minus 1. Yeah, so you move from x2 to x1, from x3 to x2, from x4 to x3, yeah, and so on. And here, from xk minus 1 back to xk, and so on, from x2 back to x3, and from x1 back to x2. So you should imagine this. Yeah, maybe I should have animation here, but like that, like that, like that, and then back, everything back. So what happens? So imagine you have on all these counters you have tokens. So each token can make 2 steps. You know, once it was transferred here, and then it's maybe transferred back. So we have b tokens here. So definitely we could only transfer at most 2 b things. Yeah, because in this phase, each token can be transferred once, and then in back phase, each token can be also transferred at point 1. But the token on counter x1, it was not touched in the first phase, but only in the second phase. So if there was something on counter x1, you know, you cannot achieve 2b because this stuff which was on x1, it only transferred once here. So in order to be able to achieve 2b, you should have x1 being 0. Yeah. And if x1 is 0, if you transfer everything fully, you actually have 2b. That's the trick. Yeah. And at the end of the day, you decrease y by 2. Yeah. Okay, so as I told you, each token is moved at most twice, and therefore that's what I already said. So maybe to apply this technique, I will show you some toy example of p-space hardness. P-space hardness is known in dimension 2, and I will show you how to get it in dimension 6. Just, so it's not a breakthrough result, but just to illustrate how you can apply this technique of triples. And yeah, so it's known that the following is known. You should believe me. So if you have 3 counter automaton with 0 tests, so reachability is undecidable. But if you ask about 2 n-bounded runs, so runs which, let's say, all the 3 counters, they sum up always to at most 2n, then it's known that this problem of having such a run from, say, initial configuration to final configuration which is bounded, it's p-space hard. So we reduce from this problem. How do we reduce? So these 3 counters in the shortest run from source to target, I mean, no configuration can be repeated. So how many 0 tests you may fire? So if you fire 0 tests on first counter, the other counters can be, second counter can be up to 2 power n, and third counter up to 2 power n. So you have in total 2 power n times 2 power n equals 4 power n possible configurations with first counter being 0 and some concrete state. Yes. So then number of 0 tests can be 4 power n times number of states times 3, because you may have 0 tests, you may 0 test first counter, second counter, and third counter. So it's enough to have 3 power times q. This is how I denote number of 0 tests times 4 power n. If you may allow for this number of 0 tests, you may, I mean, if there is a successful run, there is also one with at most this number of 0 tests. So here, I told you if I have some b, m, and b times m, I can simulate b half 0 tests. So in order to simulate 3q times 4 power n, 0 tests, I need to have here 6q times 4 power n. So if you have such a triple, 2 power n, 6q 4 power n, and then multiplication of these two numbers, you're allowed to implement 3 times q times 4 power n 0 tests. And this is sufficient for you. So in order to simulate this, at the beginning, you just increase your counters xyz by this, because I assume I have binary transitions. So this can be just one transition. And then I simulate my VASS. So I simulate 3 counter automaton on some other 3 counters. If counter automaton just increases or decreases something, UVV move as the same. And if you are supposed to do 0 tests on one of the 3 counters of the automaton, you fire the 0 test procedure and use this triple. Okay. And the end of the, so you always keep this invariant. X plus these 3 counters is 2 power n. And at the end of the day, you check counter Z to be 0, which is, you have to check that all the 0 tests were fine. You may say, okay, but maybe you have fired less 0 tests, so it didn't go back to 0. So at the end of the run, you may fire fake 0 test or something like that. You can sample. So this is how you can use these multiplication triples. Okay, so how we applied it. So first of all, this was used in our Ackermann hardness result and our tower hardness as well. And Jérôme's Ackermann hardness, not directly. Oh, yeah, I don't think directly, the same flavor. By using this technique, we also managed to prove with Łukasz some small dimension results, because I think that it's important now to focus on small dimensions to try to push further to understand small dimensions. So it's also helpful in small dimensions. And it's incomparable with other techniques of zero testing, which some of you may have heard. For example, in CONCUR, I was talking about controlling counter technique. Somehow it's interesting that these techniques are incomparable. Sometimes you need this, sometimes you need that. No one is stronger than that. Okay, so now at the last thing. Oh, I should finish now. Should I finish now, or can I go for 5 more minutes to present this?
We have until 10 for including questions. So
okay.
Feel free to do.
So just one example of push-down VASS. So I have shown you first family of examples which can have long runs up to a curve of FD long run VASSes, and then I told you, we need enforcing techniques which were helpful to get hardness. So push-down VASS is a VASS with additionally with one push-down. Okay? So there is a conjecture that reachability is decided, but we don't really know anything about this. So decidability is conjecture, and the only lower bounds, complexity lower bounds we know are inherited from VASSes. Maybe not only, but rather not much is known on top of that. This push-down VASS is equivalent to grammars with counters. So push-down, push-down automaton is equivalent to context-free grammars, and similar way counters to that. So example which I will show you will use grammars with counters, but it's equivalent to push down one. And in dimension one, you also don't know decidability. And the only lower bound you get is p-space hardness. But I will show you an example of Ackermann, up to Ackermann long runs here. So that's my point. I want to show you an example of one-dimensional push-down VASS, but phrased as a grammar, which have extremely long runs, but we don't have a way to enforce, it to really take this long run. So this is I think, a good question for future. Maybe some technique which I have showed you can be somehow applied, but probably we need something else. So in this example, I will show you a grammar with d+1 non-terminals and runs of length up to fd. Yeah, I mean, some runs have such length. But let's do it in steps. So first, very simple grammar. You have two non-terminals. You have starting non-terminal. So I will show you the semantics of that on this example. You have a rule which first outputs number n and non-terminal x, and another rule you have number -1, x number 2, and you have another rule for 0. So what is a run of such a thing? It's a derivation tree, such that if you read derivation tree from left to right, you never go below 0. So, for example, what you can do is you can fire this rule, and then you can fire this many times, and such a derivation is valid if you start from 0 and you keep reading or you start from some value, but let's say you start from 0. You read this, so you are on level n. Now you sum up this, you have n-1, n-2, and so on, and you never can go below 0. Okay, so you should have this, and then you read this. And so this is the input value, and this is the output value after traversing the whole tree, and the run is valid if you don't drop below 0. Is this explanation fine for you? I hope, yeah. So the question is, if you input, so here x inputs n. So if it inputs n, how big value it can output? So you can see, you can actually apply this rule n times, such that this n and -1, -2, and so on, this drops to 0. It cannot drop further. And then you come back and you can compute value 2n. So I hope it's clear that from k, by reading, let's say x, you can compute up to 2k. Is this example clear? Okay, so this is now very easy. Let's say now you have three non-terminals. S goes to ny, x is as before, but y can do what? -1 itself and then x on the right. So how the derivation tree can look like? I start only from y. So you input n, and you also may have something like that. So if you input n, you may have n rules like that. You go back to 0. Now you read this, you are on level 1, and now using x, you can multiply this by 2. So you can go from 1, 2, 4, 8, 16, and so on to power n here. I don't draw this subtrees here, but you may see what you imagine what can be there. So by this, you can implement like starting from value n, you can do this of size n, and then back, you can output 2 power n. Yeah, so k can be transferred into 2 power k. Yeah, do you see? So I hope you already see what can be done next. We can nest it even further. We can have z, and z can do -1, z, and y. And you have this. So you can, if z inputs n, it can fire this rule n times back to 0, then produce 1, and then fire n times function of y, so you can n times exponentiate it. So z can move, if it inputs k, it can output up to tau. And if you have more non-terminals, you can compute even higher things. But of course, here you don't have enforcing techniques for it. How to enforce non-terminals? And even if we add, some additional counter, we don't know how to enforce. With D+1 non-terminals, you may think you have weak computation of FFD, and we would like to have a strong computation of FFD. So if by adding, having Ackermann hardness in fixed dimension pull-down VASS would be already very interesting. We don't even have this. Not even in I show you dimension 1, but in any fixed dimension, it's not much. How to make it exact, I don't know. Probably some other technique. Last slide, a message. So there are many open problems. Don't think everything is solved. My personal message is we should look at small dimensions. This helps you to focus on something more concrete, which helps you often to design new techniques. And some kind of approximate message is like that. In order to get hardness, you have to find a way of, say, computing bit reachability sets or weakly computing something, and then add to it enforcing techniques. This we already have for pull-down VASSes, but we don't have this. Recent progress on VASSes was to design this enforcing techniques for VASSes. That's all. Thank you very much.
So for the reachability.
Yes.
Not invariance.
For two-dimensional, yeah.
What about for free VASS?
For three-dimensional VASS, reachability set is not semi-linear, and this example, which I have shown you at the very beginning, is already good for understanding this, because here, if you apply this n times, you can compute up to 2 power n. So you can see, if you change this into +1, you can get up to n on third dimension, but up to 2 power n on first dimension. So this is not a semi-linear behavior.
I mean, like, do you think maybe that's what separate the 2 VASS and 3 VASS? So 2 VASS is free space, right? 3 VASS may already be like, I don't know, it's maybe non-elementary. You know? I don't know.
So I'm sure maybe I misunderstood your question. You asked about whether reachability sets in three-dimensional VASS, whether they are semi-linear.
Yeah, so you said no. Yeah, right.
I said no. This is an example.
Right. Yeah. So what I was wondering is that, so for 2 VASS, it seems to be like more well behaved somehow than 3 VASS. Yeah.
Yes, there is some kind of border. Yeah.
It's already gonna be non-elementary.
That's we don't know, but might be. This is a good intuition. Up to dimension 2, things behave simpler, and starting from dimension 3, we know no techniques in which dimension 3 is easier than generality. Dimension 3 already seems like flavor of generality. Yeah.
So, just first of all, quick comment. The confusion is that if you look at the vector additional system without the states, then it's dimension 6.
Yes.
Non-similar, but only because now you have states, you can actually do these things in the dimension 3.
Exactly. Mm-hmm.
But the question that I have is, for example, you actually constructed these examples where you have kind of high waves and you kind of expand this the length of reachability. Can you apply it for some games to show, because you see that you consider just reachability, but if you consider reachability for games on vector additional system, can you actually also some whether these results can be inherited in some way, and you can prove some bounds for the games?
We haven't tried, but I mean, if you, I don't know problems from games and VASSes which are like open and prone to this kind of thing. But if you know, I would be very interested to hear what are open problems. Maybe it can be. We don't have any results.
That's my question. But there are a lot of extensions of PetriNet, so how much of your results can be extended to like some of these extensions? I was thinking, for example, of so you have Polar's PetriNets, like time PetriNets, for which there are like results for like coverability. So I'm not sure if you can say anything.
Yeah. We haven't tried. I mean, of course, all the lower bounds are also applicable, but I haven't looked into that. I'm not sure what exactly are colored PetriNets. Can they be actually reduced to VASSes, or you need VASSes with something? Are they, just more compressed, or they are more expressive? Okay.
So for time PetriNets, I know there are some techniques based on what the order to prove check coverability. So I'm not sure about reachability. If you can say anything.
Okay, we can discuss it in a break.
So I have another question. Your common lower bound, are the VASSes that come out of the reduction? Do they all have finite reachability sets?
Yeah, that's a good question. I can't answer like now. Probably no.
I think it would be interesting to study the reachability problem, assuming that the reachability set is finite.
Oh, but this is already known. It's already known that you can reduce to this case in a sense, because from Jerome's work, you know that if there is a run, there is a run of Ackermann length. So what you can do, if you have a VASS, you can construct another VASS with one new counter, or maybe a few new counters, in which first you weakly compute some huge value in this counter, and then in each step of the simulation of this new of our original VASS, you decrease the auxiliary counter by one.
But then that answers the first question, because then that is a reduction.
So then you can actually design very hard VASSes with finite reachability.
Any more questions? Okay, thank you again.
Thank you.